Hello everyone, I am Uncle Guang. Today, we will discuss a mathematical problem from the 2017 Russian Olympiad. It is a number theory problem. Let's take a look at the problem. We are required to find all positive integers n that satisfy two conditions. First, n is a composite number. Second, when we add 1 to each proper factor of n, the resulting set of integers is exactly the set of proper factors of some integer m. At first glance, this problem seems to have no clear approach. However, if we understand some basic concepts mentioned in the problem, such as composite numbers, prime numbers, factors, and proper factors, we will find that this problem is not as difficult as it seems. The logical reasoning process is concise and clever. Before we proceed with the formal solution, let's explain the basic concepts mentioned earlier. First, let's talk about prime numbers and composite numbers. If a number can only be divided by 1 and itself, it is a prime number. For example, 2 is a prime number because it can only be divided by 1 and 2. If a number can be divided by numbers other than 1 and itself, it is a composite number. For example, 6 can be divided by 1, 2, 3, and 6, so it is a composite number. We can see that all integers greater than 1 are either prime numbers or composite numbers. Next, let's discuss factors. If a natural number a can divide n without a remainder, then a is a factor of n. Referring back to the example of 6, 6 can be divided by 1, 2, 3, and 6, so 1, 2, 3, and 6 are all factors of 6. By arranging all factors of n in ascending order, we obtain a sequence of numbers, or a series of digits. Obviously, the leftmost number is 1, and the rightmost number is n. If we remove both 1 and n, we obtain a new sequence of numbers, which we call the proper factors of n. In standard mathematical terms, if an integer a can divide n and is greater than 1 but less than n, then a is a proper divisor of n. Taking 6 as an example again, the factors of 6 in ascending order are 1, 2, 3, 6, and the proper factors are obtained by excluding 1 and 6, leaving only 2 and 3 as the proper factors of 6. In fact, if we arrange the factors of n in a list from small to large, denoted as n sub 1, n sub 2, n sub k, then n sub 1 is 1 and n sub k is n. If we list all the proper factors of the positive integer n, we can find the minimum proper factor, which we call the smallest proper factor, and the maximum one, which we call the largest proper factor. Interestingly, the product of the smallest factor and the largest factor is n. We can see that n sub 1 multiplied by n sub k equals n. Additionally, n sub 2 is the smallest proper factor, and n sub k minus 1 is the largest proper factor, and their product is also equal to n. This conclusion might not be immediately apparent, but it can be easily derived. If you are interested, you can try proving it yourself. Now, we observe that n's factors always appear in pairs, but we must note that the number of n's factors is not necessarily even. Taking 4 as an example, its factors are only 1, 2, and 4, and its proper factor is only 1, which is 2. Thus, 2 is both the smallest and largest proper factor of 4. Finally, there are two important points regarding the smallest proper factor. First, the smallest proper factor of any integer is always a prime number. Otherwise, this smallest proper factor could be further decomposed into two smaller numbers, and both of them would be greater than 1. Second, the smallest proper factor of any integer n is always greater than or equal to 2 and less than or equal to the square root of n. Here's a simple proof. Now, with these basic concepts clarified, we can formally start solving the problem. We assume that n has k factors. Arrange from small to large as n sub 1, n sub 2, n sub k. Since m also has k factors, we denote them as m sub 1, m sub 2, m sub k. According to the problem statement, n sub I plus 1 equals m sub I. For clarity, let's create a table. From the table, we can see that n sub 2 is the smallest proper factor of n, and m sub 2 is the smallest proper factor of m. Both of these numbers are prime numbers, and their difference is 1. We can easily deduce that n sub 2 is 2, and m sub 2 is 3. Let's update the table. Since m's smallest proper factor is 3, m must be an odd number, otherwise, its smallest proper factor would be 2. Consequently, all proper factors of m are also odd. In contrast, all proper factors of n are even. Therefore, n must be a power of 2. Let's assume n equals 2 to the power of y, where y is greater than or equal to 2. If y were equal to 1, n would be 2, and it would have no proper factors, which would contradict the problem requirement. Now, we can deduce that the largest proper factor of n is 2 to the power of y minus 1, and the largest proper divisor of m is 2 to the power of y minus 1 plus 1. Consequently, m can be expressed as 3 times the quantity 2 raised to the power of y minus 1 plus 1. Let's update the table. At this point, we can take a break. The next step requires some intuition or experience in dealing with this type of problem. We make a bold assumption and conjecture that there are only a few or abstract expressions for the values of n that satisfy the problem requirements. In either case, we can start with y equals 2 and y equals 3 to see if any inspiration can be gained. Let's update the table again, adding the values of y. If y equals 2, n is 4, and its proper factor is 2. Therefore, m's proper factor is 3, and m equals 9. Everything looks good if y equals 3. N is 8, and its proper factors are 2 and 4. Therefore, m's proper factors are 3 and 5, and m equals 15. This also satisfies the problem requirements. If y equals 4, n is 16, and its proper factors are 2, 4, and 8. Therefore, m's proper factors are 3 and 9. However, m equals 27. And this does not match the number of proper factors of n, which is 3. We can observe that when y is greater than 4, there are no values of n that satisfy the problem requirements. If y is greater than or equal to 4, then n must have 3 proper factors, 2, 4, and 8. Consequently, m must have 3 proper factors, 3, 5, and 9. Since 3 times 5 equals 15, 15 must also be a proper factor of m. Therefore, 15 minus 1 equals 14, and 14 must be a proper divisor of n. However, this contradicts our initial deduction that all proper factors of n are powers of 2. The only values of y that satisfy the problem requirements are y equals 2 and y equals 3, corresponding to n equals 4 and n equals 8, respectively. This concludes the solution to the problem. That's it for today's sharing. I hope you like it.